Hello, my name is Mehdi. I'm going to present our recent work, which is robustness scan of digital circuits using convolutional neural networks. So let's jump ahead to the problem that motivated us to write this paper. So I'm going to talk about hardware Trojan. Hardware Trojan is a actually crucial problem in the integrated circuits and digital system industry, which has many malicious impacts on circuits. And these impacts are circuits overheating, functionality change, and the most important one, which is information leakage. So, to solve this problem, many Trojan detection methods have been investigated, but unfortunately, there is no comprehensive vulnerability analysis of digital circuits against hardware Trojan. And by vulnerability analysis, I mean a method to tell us that what region of the circuits is vulnerable, and hardware Trojan designers can insert the Trojan in those regions. So let's first take a look at some background. So hardware Trojan, as I told, are super small, and unfortunately, Trojan detection is considered a time-taking process. Many papers have uh, discussed some methods to detect hardware Trojans in the circuits, and some of them are really successful, but unfortunately they have some drawbacks. The most successful method is reverse engineering, which is really accurate, but it's really expensive and time-taking because you need to tear down all of the circuits to use this method. Thermal or dynamic power scanning also helps. It helps to detect Trojan location because when the Trojan get activated, it uses power in the circuit, and we see some unusual power usage in that region so that we can use a thermal or dynamic power scan to detect that region. As you can see, this is the Trojan schematic. There's a trigger input, which when Trojan gets triggered, a trigger input go to the Trojan circuit through trigger logic, and then it goes to the payload logic. And according to the Harvard Trojan designer motivation to build Trojan, it will do the designed functionality in the circuit. It can be information leakage or just uh, using a lot of power for some malicious purposes. So now that we know that there are many methods to detect hardware Trojan, but all of them has some problems, we can say that prevention is better than detection, right? So generally, all of the detection methods are time-taking and expensive, and unfortunately, if a circuit is vulnerable to Trojan insertion, other same manufacturer circuits are also vulnerable. And this also causes massive loss to the manufacturer of the circuits. So this problem motivated us to follow a new solution for hardware Trojan and digital circuits industry. So basically, there are some vulnerable factors that are required uh, to insert hardware Trojan in the circuits. These vulnerable factors um are white spaces, routing congestion, transition probability, and path delay. And I will explain in the following slide why these factors are really important for hardware Trojan to be inserted. So there are a few equation-based vulnerability analysis according to these parameters and some papers that use equation-based vulnerability analysis, but unfortunately they have some drawbacks. According to the equation-based vulnerability analysis, we define some equations based on these four factors, and we say that based on these equations and these factors, these regions are vulnerable and some other regions are not vulnerable at all. Okay, first of all, the vulnerability analysis problem is not a linear problem, so this is the main drawback of the equation-based vulnerability analysis. Second, we cannot say that a region is vulnerable or is not vulnerable. So the vulnerability analysis is not a zero or one problem. A region can be vulnerable to some factors, while it's immune to other factors. So the whole vulnerability analysis is not a linear problem. So what is our main contribution and our proposed flow? First, we generate the vulnerability matrix and the vulnerability heat map image for each region of circuits. Then we propose the neural network architecture to train the heat maps image and provide an output hypothesis, which is the output of the neural network. And finally, we provide robustness factor against insertion of new Trojans in different sections of the circuits, of course, instead of classical equation-based analysis. As you can see here, it's a graphical illustration of our proposed flow step by step. So, what is the next step? So, we first extract the vulnerable factors as they are the neural network inputs. Then represent each vulnerable factor in the circuit as some images. And these images are some heat maps. Each region of the circuit is an n by n squared shaped area, and by n we mean 100 because we divide a circuit to 100 by 100 square shaped area. Then for vulnerability heat maps generated for 4 different vulnerability factors. So this is the vulnerability matrix. Then I will explain what are these A's. And finally, we create a heat map which is input of the neural network. So let's explain the vulnerability factors. First of all, it's the white space. White spaces are the placed and unused gates such as flip-flops or unused spaces in the layout. The number of minimum unity space in each 3 by 3 region, and each region is 1% of the circuit, is counted. And it's also worth mentioning that the smallest unity space is defined as inf x0, which is the smallest gate available. So we count the number of those smallest gates. In the last step, the white space matrix is converted to an image heat map and then given to a CNN as an input. So this is the equation that we defined for counting the white spaces. And here you can also see the testing benchmark circuits that we chose from ICCKE 85, ICCKE 89, and ITC 99 benchmarks. The next factor is routing congestion. The routing congestion of digital circuits also plays an important role in the final vulnerability model because the hardware Trojan designers need routing to trigger the Trojan in the circuit, right? Same as the white space factor, routing congestion of each region must be calculated and described in heat map. So we define this equation to count and calculate the routing congestion, the number of routing and the routing congestion. The next factor is transition probability, and this is also important because hardware Trojan usually are connected with nets with lower transition probability, and these are the equations to calculate the transition probability of the nets. And for the simulation, we use Verilog. We extract the netlist and use an open source tool which called Verilog to routing. And by Verilog to routing, we calculated the transition probability of the nets. Finally, the number of non-critical paths is also significant in the vulnerability model because hardware Trojans and upwards payloads usually are connected to the nets on non-critical path. And non-critical paths are the paths that their delay are less than approximately 75% of the critical path. So this is the formulas for delay, and we also calculated the number of non-critical paths in those regions in a dimension 3 by 3 region. So what is our proposed neural network? It proposes CNN architecture since we have some heat maps as inputs to classify each region of the testing circuit vulnerability based on the different vulnerability factors I mentioned. Accordingly, 4 different vulnerability classes are generated based on the CNN output, and finally, the fully connected neural network will predict the final vulnerability class. We also, as a classifier, use categorical across entropy in a neural network, which you can see its equation here. Finally, different vulnerability classes are also specified for each heat map, which is a main CNN output. So uh, we define vulnerability classes to three parts: class 0, class 1, and class 2. Class 0 means that that part of circuit is almost immune to Trojans. Class 1 means that the part of circuit has some issues and needs to be reconsidered in design, and class 2 means that the region is highly vulnerable for hardware Trojans to be inserted. As I mentioned, the vulnerability analysis is not a 1 or 0 problem, so we cannot tell that some specific region of circuits are completely immune, but we can relatively define the vulnerability class of them. So this is a hyperparameter that we use in our neural network. The next step is, of course, data preparation for neural network. The testing circuits are chosen from ICCKE 85, ICCKE 89, and ITC 99 benchmarks, as I mentioned. The main input of the CNN is 4 different vulnerability factors heat maps. The various output of the CNN are class 0, 1, 2, and the different inputs of the fully connected network are the output of the CNN. So it's a sequential neural network. First the CNN, the second is a fully connected neural network. The final output is also defined for each set of inputs. We define this as a ground truth because there is no ground truth for this, and we investigated the testing circuits and we defined it by ourselves. And the final model according to this will be trained. Since we don't have too much data, we use data augmentation technique. Data augmentation is a technique that is used to increase the data by adding and combining the previously generated data. So, the final step, we'll take a look at the results. The results were computed on a PC with 4690K CPU, GTX 970 GPU, and 8 GB of RAM. However, the machine learning algorithms were trained on the GPU, not the CPU. The data set were split into training and validation, of course, the 70% for training, 30% for validation. And in this process, we use Python, MATLAB, Verilog, Verilog Sorting, Cadence, and late editor. Python and MATLAB for the neural network and the heat maps, Verilog and Verilog Sorting for the transition probability and the delay, and Cadence and late editor for calculating the number of routing congestion and divided spaces. So, as I mentioned, we have 3 classes for the vulnerability, and we also calculated the vulnerability of those regions with the equation-based method. And we also have our ground truth, so we compare our proposed method to the ground truth and the equation-based method. So you can see a number of class 0 vulnerability classes in each region, and you can easily compare them with the other method. This is the table for the class 1, and this is the table for class 2. Since most of the methods are for Trojan detection and vulnerability classes, we don't have too much choice to compare with, but we did a qualitative comparison with other studies that somehow were focused on vulnerability analysis of digital circuits. And our method is reconfigurable, needs really few samples, no resources, and has a lot of accuracy. So here we can also take a look at our graphical illustration of our results. Our average accuracy is 92.5%. On the right, you can also compare our proposed method to the equation-based method in a 3D graphical figure. They also compare to the ground truth. You can see that our proposed method is really near to the ground truth, and the equation-based method has some drawbacks. So, as a conclusion, we propose the novel digital circuits vulnerability analysis using neural networks. We have shown that the vulnerability problem is nonlinear. An accurate nonlinear model is required to solve this. We choose neural network to solve in the nonlinear model. represented the results with 92.5 average accuracy for different testing benchmarks. And finally, we compared our proposed model to the previous case studies. The future work will mainly focus on different Trojan types, vulnerability analysis. Thank you very much for your time and consideration. If you have any questions, please ask. I would be glad to answer them. Thanks.